Okay, I'm glad you all made it in the morning. Thanks for coming, and thank you for inviting me to talk here. So yes, I'll be talking about deep reinforcement learning. And to talk about that, I first wanted to step back and talk about the big picture. Why do I care about deep reinforcement learning? Maybe why you want to care about deep reinforcement learning. That's of course up to you to decide. But I wanted to step way back and start at the Industrial Revolution and what they sometimes call the machine age, and think about what that was, what happened there. And essentially one way to think about this is that this was a time in which we took manual solutions that we used to do with manual labor and then replaced that with machines. This is where factories and such came into play, steam engines. And then later, in the digital revolution, more recently, or the information age, essentially we did something very similar where we now took repetitive mental solutions and we replaced those with machines. So one example of this is a calculator, where we know how to calculate things by hand, but you could also automate that process if it's formal enough. But it's an implementation of a solution. In both cases, we do have to come up with a solution first, and then we implement that solution. Now, what I want to then posit, which might seem obvious now, is that the next step should perhaps be that we only specify a goal and we leave the discovery of the solutions to the system. This is what learning is, and this is what you might call the AI revolution. This is a very broad sense, so let's dive a little bit deeper into what AI then might mean. So back in the day when people started talking about artificial intelligence, a lot of the first approaches were symbolic, where we could then reason formally about things that might happen or things that might imply other things. And this is already an automated form of reasoning. You could come up with new conclusions based on the information that you put into the system. But the rules themselves were programmed in advance and static. And often there was a high level of hand-picked knowledge formalism or level of abstraction, if you want to think about it that way. With which I mean you had to basically pick what the symbols were, what they meant, how they would interact with each other, and then you could derive things. But there was a lot of specialist knowledge in some sense involved. And one thing that happened with these systems is that in many of the cases they basically didn't scale that well to messy data as you would have in the real world and to uncertainty. From a different perspective, there's classical statistics. And in classical statistics we are able to deal with uncertainty, with messy data. But typically the classical goal in statistics is, it's already in the name, it's to basically get statistics about your data. It's about analyzing. And then the decisions were still made after the fact. So you would analyze something, and then based on this analysis you would learn something about your system or whatever it is you're interested in, and then you could make decisions. And even picking what to analyze in the first place is a decision you do up front. So there's something in here which you could already call learning. This is the automatic analysis of the data, but it's not completely end-to-end from observing something to making decisions in the world. So again, here I posit something, and this is just to make you think if you agree with that phrase. True AI should learn to make decisions autonomously. This kind of makes sense in a reinforcement learning context, of course, so this might not be a very surprising thing for me to say. So on that note, we go into reinforcement learning. And I first just very briefly wanted to recap some things that you were covered yesterday, so that I'm sure that we're all on the same page. Whenever you have any questions, just feel free to raise your hand, and I'll try to look around sufficiently to spot you.
Quick question.
Yeah.
Where would you?
Good.
In the previous slide, where would you put control both classics and statistics and Bayesian networks? Where would you put them in the previous one?
So it depends a little bit on what you use, for instance, the Bayesian networks for, and but in some sense, maybe in the strict, like if you consider it in a narrow sense, you could view the Bayesian approaches as the analysis, but then you still might come up with decisions yourself based on this analysis. There's a little bit of a gray area there, of course, because you also have Bayesian decision theory, in which then decisions are kind of automatically determined. And there's of course a lot of other gray areas. For instance, in statistics, a well-known area is active learning, which is all about sampling, which you could say are decisions. The control problem is an interesting one as well, because sometimes when we say control, especially in the more classic approaches, we basically assume we have full access to a system, and we basically inspect the system and then learn what a good policy of control is for that system. So there is not maybe a lot of learning happening there, it's more inference. In that sense, reinforcement learning is a little bit different because we definitely, I mean, learning is in the name for a reason. We're definitely focused on the learning part. Thanks, very good question. Okay, so this is just a recap. What is reinforcement learning about? It's a framework for making decisions. And this is maybe slightly subtly different points than others have made before, because I really want to focus on it as a framework. In addition, there's a lot of algorithms that fall under the header of reinforcement learning, but to me, reinforcement learning is more than that. It's about the reasoning framework in which you can reason about what it even means to make decisions and why you would even want to make certain decisions. The general setup that we're thinking about is that there's an agent or an actor that interacts with an environment and sends actions out into the world, as you could see. And then observations come back in. Either passively, it just comes in at a certain tick rate, maybe, or maybe actively you pull in observations whenever you have the resources to do so. And then in this talk, I want to focus mostly on learning to act, which might seem obvious, especially given what I said before, but I wanted to contrast that to what Rich Sussan was saying yesterday, where you could also think about reinforcement learning as being the study of learning to predict. And maybe it's both. But in this talk, I'm mostly going to focus on learning to act. So there's a certain goal here, which is to find a policy of behavior that is good for some certain goal that you want to specify. So each of these actions that the agent sends out can change the state of the world and also can result in a reward. I deliberately did not put the reward in this little diagram. You've probably seen many versions of this diagram. I know there were like at least 3 different ones yesterday. And oftentimes you see the reward coming from the environment into the agents. And that's definitely a valid way to think about these things. If you have a certain task, it's easy to think about these things as generating the rewards that your agent should then optimize. But sometimes it's actually more natural to think of these rewards as internal to the agent, that the agent likes certain observations. The observations might, in some sense, carry the information that you need to infer the reward, but the world out there might not care about which things you prefer. So there might be many signals in your observation that all might be taken to be rewards, maybe also different rewards by different agents. And maybe in that case the reward lives within the agent. Most of the algorithms that we talk about in reinforcement learning don't particularly care where the reward comes from. They consider it to be external to the learning algorithm. But it might still be internal to your agent. And then the goal is, to pick one, to optimize future rewards for some reward signal. So there's many examples. We saw several yesterday. We'll see more today. Just as a reminder, things like video games have been done, board games. Robotics is an application area of reinforcement learning. Recommender systems, there's many more, and there's more each day, more or less. And essentially this is because you could think about all problems that involve making decisions and or predictions about the future as falling under the general header of reinforcement learning. So that makes it a very general field, and many of the algorithms are also intended to be very general purpose. It also means that you might actually be doing what I would call reinforcement learning without necessarily realizing that you're doing reinforcement learning. But as long as you're making decisions, and these decisions might impact the world in some way, and especially if there's time dependencies and decision making in the same problem, then I would say this falls under the header of reinforcement learning. So now I wanted to talk about what approaches you could take to reinforcement learning. So the goal is, to reiterate this, we've specified the goal as to learn a policy of behavior that optimizes something that we'll talk about more. That means that there's at least 3 possibilities, and potentially more, but these are the main areas that you could think about. One is you could learn the policy directly, and Peter Abel talked about this yesterday at quite some length. I'll touch upon it briefly again today, just to remind you how you could do these things. Separately, and this is also something that was talked about at length yesterday, for instance by Rich, but also by Joel earlier. Excuse me. You could also learn values, and these values could then capture what you predict the reward will be. And then if you have these values, it actually becomes fairly easy to also infer a policy. Essentially, if you learn action values, you can just infer a policy by inspection. you pick the highest valued action in each state that you're in. A different approach, which we haven't talked about much yet, as much yet at least, is to learn a model of your environment. Maybe it doesn't have to be a precise model, but maybe it's some abstraction of the environment or of the task that you want to solve. And then maybe you can infer a policy by planning. This is actually the more classical approach, where maybe the most used way to solve such systems is by actually not learning the model, but constructing the model, and then doing planning on top of that. And planning and search are very rich research fields and still very active. And there's many interesting questions there. Even if you have a model. Of course, it becomes extra maybe interesting, but also complex if you have to learn the model as well. And maybe you cannot trust the model fully to be exactly what you want the task to be. So that means concretely that you have to have one of these components in your agent. You either have to have a policy explicitly, like a function that maps your current state of your system to an action. You have to have a value function, or you have to have a model. Maybe there's alternatives, but these are the main components that we typically consider. You could also have combinations of these. So it says at least one of these components. Just to give you an example, if you have both a policy and a value function, this is what we often call an actor-critic system. The actor is then the policy, the critic is then your value function. And we've seen examples of this yesterday. I'll also briefly give you more today. So just recapping some notation, this is commonly used notation for some of these things. Actually, for models are more out there. Sometimes people just use f as a function for the model. Rich talked about Q values. Sometimes you see a capital Q. These days, more and more often you see a lowercase q. But this is the notation that I'll mostly stick to in these slides. There was a question. Yes.
So given a problem, how to approach, how to decide among the three approaches? So could you comment on these, like management, all the three approaches?
Yeah, so it's a very good question. If let me phrase it so that you can check whether I understood correctly. The question is, how do you pick which of these things you learn? And that's essentially an open question. And one thing that we've noticed, let me just give you a little bit of a teaser as well to the deep part. Until recently, a lot of reinforcement learning was done not in the context of deep neural networks. And then it was kind of common knowledge that the model-based approach was definitely the most data efficient one. It takes maybe a lot of compute to learn a model, but it's very data efficient because you can put all the information that you get from the world into your model, and then you can just plan with it. This is where the compute comes in. The planning might take you some compute. Somehow we haven't really been able to replicate that yet with the deep neural networks, and I'll talk about reasons for that as well. Both the direct policy learning approaches, and Peter Biel talked about this quite a bit yesterday, are very successful, but also the value-based approaches are very successful. It might be a little bit problem dependent. There might even be, these things might be more related than we realized in the past, and there's been some recent work that showed that these things maybe are quite closely related depending on how specifically you implement them. But it's a very good question, and it's basically one of the main topics that we're researching to figure out when to use which method. Fortunately, they're all, the methods that I'll talk about are typically quite general purpose, so even if you pick the wrong one, it doesn't mean that it won't work. It might just be maybe slightly better if you use a different approach. Okay. So all of these components are essentially functions, and we need to then represent and learn these functions, whichever component you choose to put in there. And this is where deep learning then comes in. So now to switch to deep reinforcement learning, this is essentially the study of using deep learning to learn policies, values, and/or models to use in the reinforcement learning domain. And again, this is actually a fairly broad area. And as I said before, you might actually be doing reinforcement learning, or at least what I would call reinforcement learning, without necessarily thinking about reinforcement learning or using the canonical algorithms that we think of when we say reinforcement learning. As long as you're using deep learning and somehow you're making predictions about the future and making decisions that might optimize something, you could say this falls under the general framework of reinforcement learning. And then it might be useful to also figure out what has been done in this field. Something beeping. Okay. So to recap, reinforcement learning provides a framework for making decisions and predictions. Rich would get upset if I didn't say that. And then deep learning provides maybe a toolbox, this is one way to think about it, to learn these components. And together, this is sometimes posited as something to think about. I'm not going to commit, I put a question mark. Is this sufficient? Maybe, maybe not. I haven't talked about a lot of important details, right? I haven't talked about, say, memory. I haven't talked about knowledge, maybe more generally. But these can fit within the, under these headers. And then the question is this enough for AI? I'm not going to commit, but I encourage you to think about that, especially after all of these summer schools have concluded. But concretely, we're just going to do RL, where the components are now deep neural networks. So now basically my talk is done, and you can all go do something else. Well, it's slightly more subtle than that, slightly harder. And I'm going to dive a little bit into depth into some of the methods that have been done, and partially to make you aware of what has been done, but also partially to make you aware of some of these problems and issues and interesting research questions that pop up when you combine deep learning with reinforcement learning. To start off, I'm going to talk about deep Q networks. And to do that, first I'll quickly recap what Q learning is. So this is the Bellman optimality equation, which was phrased by Richard Bellman in the 50s last century. And this is an equality. So this is essentially, you could say, a definition. Q star here represents your optimal value function. What does optimal mean? This is the value of the policy that will get you the most rewards in this system. There's an expectation here, and the expectation basically spans any randomness that might occur in your reward function and in the transition to the next state, which is called st plus 1 there. This assumes that this is a Markov decision process. It assumes that all the information that you need is contained in the states. Joel talks a little bit about what that means in practice, and also like formally what that means. But if this is a Markov decision process, this is an equality. And you could also use this. You could do dynamic programming to solve for this optimal value function if you don't know it in advance. And essentially when the equality starts to hold, then you know that these must be the optimal values. This only works, you can only do that if you have access to the model. This is exactly what dynamic programming does. But we can turn this into an algorithm, a temporal difference algorithm, where essentially we just sample this thing within the expectation, and then we make a small step. So the formulation I've written down here is the tabular formulation. So you can just think of this as there's an entry in a table for each state and action separately. And we just take a small step whenever we enter this state and take that action towards this target. The target here being the reward plus the discounted value of the next state. But the value of the next state here is defined as taking the maximum value over all of the action values in that next state. This follows from the optimality equation up there. It also makes a little bit intuitive sense if you think about it this way. We're trying to approximate the value of what would happen if I take this action and then I take greedy actions with respect to my current values. Taking the greedy actions with respect to my current values is sometimes called policy improvements, because this should give you a better policy than if you, for instance, take random actions. And then the learning of the values here is sometimes called policy evaluation. In the Q-learning algorithm, these things are wrapped into one update, where you're essentially doing evaluation and improvement more or less in the same step. This is very similar to value iteration in dynamic programming. So now we have a sample-based algorithm that can learn these values, and these will give you approximations to the optimal values. And you might not want to wait all the way until you get the optimal values. It might be good enough to be good enough. If you have an estimate of these optimal values, this might already give you a good policy. This is an off-policy algorithm, with which we mean that it actually learns about a policy that might differ from the policy that you're following. And this is what I meant when I said you're learning about the greedy policy with respect to your current values. The greedy policy is just a policy that picks the highest value action in every state that you bump into. So the greedy policy with respect to your current value just uses your current value estimates to do that. What's nice about this is that it doesn't really matter what data you throw at it. That's not completely true, but it can learn about this even if you explore. And that's very valuable, because it means if you, for instance, have a lot of data, you might be able just to go through that with this algorithm and still learn about the optimal values, even if you didn't follow the optimal policy while you were collecting the data. And off-policy reinforcement learning is also a very rich topic with a lot of application areas. Yeah?
Can we come back to the previous slide?
Yes.
So I'm just a little confused about the notation.
Sure.
You're using smaller s, and can you just like define what the smaller
Things random variables because we're sampling.
Okay.
So this is no longer for any state in action. This is an update specifically for the state in action that you happened to be in. So so maybe I shouldn't have used an equality there actually, but it does still hold because now it's no longer the same function, because you can see all the way at the left it says qt plus 1. So this is essentially the values after the update. So in that sense it's well defined, but it might be a little bit confusing the way it's written down.
Thank you.
Good question, thanks. Yes?
Is there a reason that there's a discount factor in the second equation but not the first one?
Yes, it's because I forgot to put the discount factor in the first equation. Sorry, very good question. I actually deliberately first didn't have discount factors anywhere because I just wanted to basically defer talking about those, but then because they were already covered yesterday, I start plugging them in. I missed one, sorry. So there's no reason that there's no discount factor in the first one. Good question, thanks. Yeah?
So you say learning can kind of learn off policy no matter the data, but that's semi-true yet.
Yeah.
Any kind of like rule of thumb as to how, like if I collect random data, can I do like efficient learning, or I eventually need to have some algorithm that knows what it's doing?
So this is a very good question. So the question is essentially, do I need to know anything about the data that I'm collecting in order to be able to do Q-learning? Are there maybe some constraints on the data? Can you just do anything? Or I'm going to give two answers for that. First answer is the theoretical one, which holds for the tabular case. And in this case, it's actually sufficient that you cover each state and action pair infinitely often in the limit, and then you will learn these optimal values. That's a pretty strong result, because it means you basically don't care at all what your data distribution is, as long as it covers everything. This only works in the tabular case though, because if you're going to do function approximations, you're going to generalize. This is the whole point of function approximation. And that means that if you're going to sample certain states' actions more than others, you're essentially going to weigh the approximation error that you're going to end up with your data distribution. So if we're going to do deep learning with reinforcement learning, it's actually very important to sample your data in specific ways, and I'll have some concrete examples of that later on. Very good question. Okay, so now this is just to reiterate, we now have a way to approximate these optimal values. And just to point out what might be obvious, but just good to be explicit about this, we can now essentially get an optimal policy if we have these optimal values by simply selecting the highest valued action in each and every state. Actually, this might not be completely obvious immediately, but it is true. And it's good to, if you're interested in this and learning more about this, it's always good to refer to the classics. So the Sutton and Bartow textbook gives a very good introduction on this. Okay, so we were talking already about deep reinforcement learning. So where's the deep? Well, here it is. Deep here just means you have a multi-layer neural network that represents this Q function. So my notation here now is that there is a Q value which takes a state and an action and some parameters W. These parameters are just all of the weights in your neural network. I've just condensed them into a single bolded variable here, a vector which contains all your parameters. And then one way to do the updates, the Q-learning updates, is essentially to change these parameters. So I put delta W there. This means I'm going to change my parameters. And I put an equality, but maybe it's better just to think of this as kind of proportional to the quantity here at the right-hand side. Alpha is a step size here, so it's like a small number here. We're going to take a small step. This is important because the function that we're using is nonlinear, and then a big step might actually ruin your function. It's also important because the data coming in might have noise. So you want to average out this noise, and therefore you want to not choose too big a step size. The quantity within the brackets is exactly the same as before, but now using my new parametric Q function as my approximation. And what we do to update the parameters is simply to multiply this with the gradient of my Q function with respect to the parameters. This is a fairly simple update rule. There's something a little bit odd about it, and I don't know if anybody noticed. If you noticed something a little bit odd, maybe you could raise your hand.
Why is it evaluated at 80 and not at the maximum?
Why is it evaluated at 80? This is because this is the update to the weights after taking action 80 in state ST. And this is essentially the value that we're going to update. So we're not interested in updating only the value of the maximum action at state. In fact, we can't even, because we haven't perhaps taken that action. So we might not know anything meaningful about this. So if we go back to the Bellman equation, this is conditional on the state and the action. So the target here is also considered a target for the state and action pair. This is why we're updating that value. But did that make it clear? A little bit. Okay. Yes?
The maximum relative with reading action, why is it with the current weights and not the weights that you will have? Like, why is it that you will have the next step inside that you will?
So why not take the next W on the next step is the question. Is that right?
Or why don't we take the next W? Why do we take the current W?
Well, this is an update for the W, so why don't we take the next W and not the current one? So first thing to just to be very clear, there's one set of weights here right now. So there's just a neural network with some weights. So the weights aren't dependent on states or anything like that, just to be clear on that. And then to be clear on what this update is about, this is about updating the weights. So in order to update the weights, the next weights aren't available yet. This is exactly what we're going to use to get the next weights. But having said that, there are actually algorithms that kind of do this, where they first do kind of a partial update, then revisit the update and redo it. And sometimes you can get some gain from that. They're not very common in deep reinforcement learning because essentially evaluating one of these functions is not completely free. It's not very expensive. These networks aren't huge, but you don't want to do too many forwards if you can help it. Yeah?
I just missed something. Could you explain why the weights and the states aren't the weights how we're parameterizing the state action pair? So what's the state mean outside of the weights?
So yes, very good. The question is how are the states different from the weights in some sense? So one way to think about this, I hope this clarifies, is that the state that I put in here as an input to the function is essentially your observation of the world. It could be a little bit more than that. It could also be the memory of your agent in addition to the observation of the world, if you will. And then the weights are just the parameters of your function. Yes?
Are all the parameters of all the layers into the same vector?
In this notation, the W here contains all the parameters of all your layers, just to simplify the notation. Yes?
Backpropagation to the layers.
Well, the way to update this, you still do backpropagation. This is a standard update, and actually, let me maybe just flash this up. You could also just interpret this as a certain loss, where we basically have a squared loss, where we have a certain target, y, and we're updating our parameter q function, which I now denoted with a small q. And I apologize, but I changed the weights here to thetas. I should have made that a w. In literature, it's actually very common to use theta for the weights. I wanted to use w, but so these are just the parameters of your network. So this is the same q function that we had before. And then one way to interpret the exact same update that we had on the last slide is basically we're doing stochastic gradient descent with this loss, where you basically plug in a certain target, which happens to depend on your estimated q values as well. But otherwise, it's just a target, and we're just updating, we're regressing towards that target. There was a question? Oh.
Why did you get the gradient with respect to W in line?
Why aren't we considering the gradient with respect to the parameters in the state that we're bootstrapping on? That's an excellent question, and this is actually what I was referring to when I was saying there's something slightly odd about this update. And there's a good reason for this. There's actually multiple good reasons for this. So there's one good reason for this is if we get rid of the max for a moment and we consider the actual action that you take in the next state, then this becomes the Sarsa algorithm, or basically just the state action version of TD. I say that just to get rid of the max. Let's just forget about the max because it's nonlinear for now. It's a very similar algorithm otherwise. And you could think about also taking the gradient with respect to the value of the next state. But what would that mean? That would essentially mean that we're updating the value of the next state to be a better target for my update of the value of this state and action. That kind of violates causality, because in some sense we want to know about the future, and not necessarily we want not to make our predictions in the future to be better so that our predictions in the past were somehow better already for these. There's also a practical reason. The algorithm that does take the gradient with respect to these parameters in the next states actually tends to work less well in practice. So it seems that there's some truth to this causality argument, at least. Yes?
Can you explain why minimize this loss connect to the Bellman optimality, connect to the original Q-learning equation?
Yes. So why does minimizing this loss connect then to the Q-learning equation? Well, we could think about just think about sampling this loss, which basically means you just have this one square term. You have y minus q squared, and then half of that. So if we want to minimize this, one way to minimize this is just to take the gradient with respect to this. Oh, sorry, the gradient with respect to our parameters of this loss. And then take one step to minimize. Then you get exactly this update. But also, if you just think about what that means, it means that we're going to essentially move our action value function, our Q function, towards a situation where my Q function at the current state action pair in expectation equal the next reward and then next state value. If you manage to minimize this all the way to 0, of course if you're doing function approximation this is typically not possible, but in the tabular case you might actually be able to reduce it all the way to 0, and if you would reduce it all the way to 0, essentially you get exactly that Bellman equation back. One way to see that is you could move the Q value there on the left-hand side of the equality to the right-hand side. It gets a minus term then, of course. And then you could square that term, and if that becomes 0, that means that these things must be equal. So if you're able to minimize the loss fully, you kind of get the Bellman optimality equation. I say kind of because, of course, if you're doing function approximation, you're not going to be able to reduce it all the way to 0, and you're not going to get the equality exactly. But you still get something related, and this is the goal. Yes?
Yeah, I remember in the nature paper, this loss is collected into -1 and 1. Can you explain that?
You're asking about the specific, in the nature paper, there's a slightly different update.
Yeah, so in the nature paper, the loss is collected into -1 and 1. So I don't understand why we do that.
So I'll talk about that in. Ask again if it's not clear after a few slides, but I'll go into that. Okay. So just one more thing I wanted to say about this is that the targets are now basically considered a constant, as we discussed that just now. So we're not taking the gradient with respect to the parameters in the targets. This is very easy to implement in current day frameworks. For instance, in TensorFlow, you might just put a stop gradient on the target, and then your gradients don't flow into there, and it's very easy to implement. So to continue, indeed, so in the Nature paper on these systems, there were two slight changes to this. Important changes. One is, if you compare this first equation here to the second equation on the slide, there's a difference, and the difference is in the parameters at the next state value. There's a new quantity here, this W, which I made red with a minus in the superscript. And what this W is, it's essentially a copy of your parameters, which is then kept fixed for a while. So in practice, what happens, every few thousand steps, we would just take the parameters from the network, we just copy that, and then we can keep them fixed for a few thousand steps, and then after a few thousand steps, we repeat that again. So why would we do this? Well, if you don't do this, and I'll talk about this a little bit more, your targets essentially become non-stationary, and this turns out not to work that well with these deep networks. The deep learning doesn't like it. A different thing that was also done, this relates to a question that was asked earlier about the data distribution, was experience replay. So what we normally consider when we first explain reinforcement learning, and what was also very commonly done, and still is in some cases, is to learn online. So you basically act, you get your data, and then you use that data to immediately update your Q values or your policy. And this is very appealing, I think. But you could also, of course, store the data that comes in, and then just replay this to learn more efficiently from the data. Essentially, you just collect some data as if you're building a data set, and then you're just learning more and more from this data set. And in the DQN algorithm, this was done by creating a buffer of transitions. And the number of transitions in there is not maybe vitally important, but there were like 1 million transitions in this buffer, and then just sample from this uniformly. This does mean that we're sampling from a policy that is a little bit outdated on average. But that's okay, because we're doing Q-learning, so we're learning off policy anyway. And what it does is it makes your data distribution more diverse. So it's a little bit closer to the typical IID assumption that is made when you do standard supervised learning. And again, it turns out that the deep learning algorithms maybe work better in this case. And this is a general theme that you have to realize that many of these algorithms, especially in deep learning, were developed with a certain, in a certain context of classification or regression. And many of the things that work really well there might not necessarily transfer if you're going to violate some of these assumptions. For instance, if your data distribution is no longer IID. So it's good to be aware of these things and maybe to also adapt things a little bit to make it more similar to the regime where we know these algorithms work well. Yes? Sorry, how we fill the replay buffer. Essentially what happens in the standard DQN algorithm is just there's an agent taking actions in these Atari games, for instance. And every transition, which is then a state, an action, a reward, and a next state, gets stored in this replay buffer. Of course, you could do this efficiently by just storing a sequence, so you don't have to duplicate states both at the beginning and at the end of a tuple. And then the learning was actually completely from the replay buffer. So the online data was put into the buffer, but the learning algorithm would read from the buffer, wouldn't see the online data immediately. And on average, each sample would be looked at more than once. So on average, you would see a sample 4 times, but there might be a few samples you never see. There might be a few samples which get replayed more often. And I'll talk about that a little bit more in a moment. But first, I wanted to talk a little bit more about this target network. This is how we call that network which depends on these copied over weights. I copied this slide over from Vlad, and I see he's using the theta. So don't get confused by sometimes it's a W, sometimes it's a theta. These are just the parameters of your neural network. It's the same thing. And you can also ignore the subscript I here for simplicity. So this is essentially just the same thing as we had before. Phrased here as a loss. So it's like a squared loss where we're taking the gradient with respect to the current parameters. So what's the intuition here? If you would update the parameters and you would have them both at the next state and at their current state, the same parameters, then even though you only want to update the value at this state, you'd kind of automatically also update the value at the next state. And this is especially true if you consider something like this, an Atari game, as depicted here at the bottom right. The frames might actually look very similar from one state to the next because we're acting at a fairly fast frequency, taking about 15 actions per second. And that means that actually these values might be generalizing, they might be flowing over into each other, which means that if you update the value at this state, almost automatically the value at the next state also changes. And this might make your learning quite unstable. So this is the whole intuition behind this target network, where we keep these weights fixed a little bit, is that we update the value at this state, but then the value at the next state isn't automatically changed. And this just makes everything a little bit more similar to regression, to things that we know that works. And it does really seem to help performance quite a bit. There was a somewhat surprising later finding, is that if you have a bigger network, with which we just mean you have more parameters in your network, more hidden nodes, this is less of a problem. And this kind of makes sense if you think about it in terms of generalization, because now the network has more capacity, so it can also maybe see the differences between these very similar states more easily. And therefore, if you change the value at this state, it doesn't automatically change the value at the next state as much. If your network is smaller, it needs to generalize more across all of these states and actions, and therefore you have more of this effect. Yes?
When do you update the states to the several steps?
So typically what we do when we, the question was when we do update the states, there's two answers to that. First, there's the acting of the agents. Here the state automatically changes whenever you pick an action. So the state is just whatever the system provides you. In this case, it's a frame of the Atari game. These are put into the replay buffer. And then what we typically do in the DQN setup is we sample a mini batch from the replay buffer. We do an update with that mini batch. We toss all of them away and we sample a completely new mini batch. You could also keep the same states and do like a couple of updates, and this might work well. I don't know that anybody's tried. Yeah?
Do you observe that the use of the target network is less necessary in later phases of learning as your network is getting towards convergence?
So the question is the target network more important at the beginning when all your values are basically crap? Or, and maybe less important later when your values have improved? I don't know. It's an interesting question. Maybe you're able to get rid of it more and more later in learning. And there's some benefit if you could, because it could speed up the process of propagating the information. Because if you're going to keep these weights fixed for a little while, this does mean that like newer updates aren't yet in those weights. So it's a good idea to maybe investigate. Yeah?
Is bootstrap, I didn't realize that bootstrapping related to aliasing. If your system aliases anyway,
Yeah.
whether you're bootstrapping or not, wouldn't it fail, or is aliasing only an issue because of the bootstrap?
That's a very good question. The question is essentially how do bootstrapping and aliasing or generalization, how do these things interact with each other, and why am I focusing on it in some sense? There's definitely an interaction here because consider the Monte Carlo case where we would do full rollouts. Let's just consider prediction, so forget the off-policy bit here. You could still consider doing bootstrapping or getting a full Monte Carlo rollout. And you could still consider doing generalization, so doing function approximation. The aliasing, the generalization here is important, how much you alias, because the learning the guess from the guess actually changes not just your bias variance trade-off that Rich Sutton talked about yesterday. It's in some sense. But it also changes exactly what the capacity is of the target that you're bootstrapping on. So in some sense, there's a more formal way to talk about this as well. And one thing that's been investigated quite well is temporal difference methods with linear function approximation. And there you can actually show that the fixed point, so the eventual solution that the system converges to, depends on how much you bootstrap. If you bootstrap more, you're going to actually end up in a different answer all the way at the end even than if you don't bootstrap at all. There's a trade-off there where learning is still faster with bootstrapping, but in the end, the actual solution you get might be eventually better if you would just do the Monte Carlo thing. Doing pure Monte Carlo is very data inefficient, so we wouldn't want to do that. Of course, here's a different thing that's going on, which is the off-policy learning, for which we kind of maybe need to bootstrap a little bit more than if you would just be doing predictions. So there's another confounding factor there. Okay. Yes? That's a good question. So the question is, how do you decide what to keep in your replay buffer? And this is a little bit of an under-investigated topic, I think. What was done was just the most recent million frames. And this does bias you. It does bias you towards what your policy has done in the somewhat recent past, and this might not be the optimal way. It's related to something else that I wanted to talk about just now, which is also related to the experience replay. Because in addition to deciding what is in the replay, even if there's lots of stuff in the replay, let's go to the extreme and let's say we never toss anything away. We just put everything in the replay. Then there's still this question, which is very related to the questions you were asking. Which things do you pick to even learn from? So the tossing away of data is similar because if you throw it away, you can never learn from it again. But even if the data is there, it doesn't mean you actually have to learn about each sample equally much. And there's benefits to doing experience replay, which were quite clear from the results. So first to recap that. It's more data efficient because the data is used more than once, on average 4 times in the standard DQN setup. and it resembles supervised learning more, so for this reason the deep learning probably works better. This is just a list of improvements that were related on the DQN, which I won't go through step by step, but I'll highlight a few. And this is going back again to that question about the data distribution and the experience replay. And one thing I wanted to highlight first is that we can basically think of this replay differently. We can think of it as a non-parametric model of the environment. And there are some benefits to thinking about it this way, because now if we consider it a model, we can think about querying the model. It's a non-parametric model, so you don't actually get from a state in an action what the expectation is over next reward states and so on, but you get a sample from this, the sample that you actually saw in the past. And there's then multiple ways you can use this, and I wanted to highlight 2 examples of this. One is to sample non-uniformly. I was already pointing towards that. And this is called prioritized replay, and this really helps a lot in terms of performance. And one way to do that is, first let me mention the second one. You could even use this model to kind of plan. So in some sense, you could, for instance, look at a state in an action. You could look at what happened then, and you could take this as an indication of what might happen again if you're in a similar or in the same state in action. And maybe you can even compose these things together. This is not yet a fully fleshed. I don't think the last word has been said about this research. There's a lot more that can be done. Also, especially when you want to maybe then distill this down into a parametric model, which is a very interesting avenue, I think. But to talk a little bit more about this prioritized replay, so what, for instance, could you do? You could do something which is fairly simple. You could store the temporal difference error of each of these transitions, and this is basically a snapshot of how much would you learn from this transition. And then when you sample it, you might learn maybe this amount. But it also gives you an indication of maybe which things you want to sample. Because just consider the situation where this temporal difference error is 0, which means that just by chance, the state action value that you had here accurately predicted the one-step reward and the resulting state value that you end up in. If you're going to sample this from your replay, you're going to learn exactly nothing, because your error will be 0 and your update will therefore be 0. That's obviously a waste. If instead you pick something where this temporal difference error is high, you're going to do a comparatively bigger update to your weights. In addition, this is kind of the stuff that you want to learn about, because these are the transitions that were where your values were inaccurate, and thereby, if you learn about these, you might learn more about the world than you would otherwise. This is just one way to prioritize, and you have to be careful a little bit how to pick this, because the Atari games are actually deterministic. So if you do in a certain state, do a certain action, you deterministically end up in the next state. This is more or less irrelevant to most of the learning algorithms, but it's relevant, for instance, for this part, because if you consider a situation where there is actually a very noisy environment, if you would use exactly this prioritization, it might just replay the noise a lot, especially if the noise is non-uniform. There's some very noisy transitions and others aren't. So then maybe you want to tweak the prioritization, but you might still want to prioritize your replay if you're doing experience replay. A different thing that I wanted to highlight, but yeah, and question first.
An idea of that would be, can we put another RNS model on that, what to pick and what not to pick, or what to pick for and then work on that?
Yeah, so could you learn maybe which things to sample, which things to look at? This is definitely, yes, I would say. How? Less clear. Would be an interesting area of research. I don't know that a lot has been done there yet. It's a good question. Yeah.
For a comment on your previous slide, so for example, these 2 graphs on the right, they probably represent like maybe a few hundred iterations, not hundred iterations, but like independent games or samples. But there's no error bars, and that's something that throws me off quite a bit in some of the your papers. It would be great if maybe they all within one standard deviation from each other, or not. I don't know. Maybe you can comment on that.
Yeah, sure. So there you often see many of such curves, and indeed often there aren't error bars. In practice, this is often the case because there is only one seed. So you might run. So what we typically do, we take like 57 Atari games, or these days at least, and in the Nature paper it was 49, but we added a few. And then we run these algorithms on all of these games. And one way to think about it is that we're kind of doing an analysis on the whole set of games. So we're still doing 57 different things, but we're not doing, say, 30 samples per game. Ideally, we would, right? But it's just so much more compute. That's.
So do you only, let's say you do 5, or you only take 1 seed and that's it, or you take the best seed for?
Oh no! So yeah, no, we don't take the best seed. We just take 1 seed, and then we take whatever that gives you. Taking the best seed, I would say, is much more dodgy.
Yeah. Great, thank you.
There are different approaches. So in some cases, some people have, for instance, done random hyperparameter search. And then it becomes a little bit more gray area. Sometimes you just want to pick the best hyperparameters. We have to be a little bit careful because you might be maximizing over things. So then what's often done is you pick basically the best couple of hyperparameters. And then maybe you pick like what are the third best, like the 3 best. And then it gives you some sense of how robust the algorithm is. But yeah, the details are often phrased explicitly in the papers. But as I said, we would love to do these things maybe with a lot more samples, but it's prohibitively compute intensive.
It can throw you off because there's a lot of variance when you're doing reinforcement learning, especially
Yes.
in natural games, and then you sort of look at these results and you're like, oh my god, I can achieve like X, Y, Y, but normally you're above or.
So there's some variance definitely. So you shouldn't pay too much attention to like the specific numbers too far down to the right hand side of the number. In my experience, though, there's many games, such as Pac-Man is a well-known one, or Miss Pac-Man, where these learning curves are actually very consistent.
Okay.
And if you improve your algorithm, you get a learning curve that's basically consistently above the other one. And if you have a bug in your algorithm, it's basically consistently not learning. So these games are apparently a little bit more robust to these things than I would have expected maybe beforehand, before working with them. But it's definitely something to keep in mind because this doesn't hold for all domains, and for other domains it's going to be even wilder. It also depends on your algorithm a lot. Some algorithms are more susceptible to these things, to noise in some sense. Yes?
So you mentioned the seed. Are you talking about the environment seed or the model parameter seed for the learning?
So the question is, we're talking about the seed for learning or the seed for the environment. I typically mean there's just like, for instance, you might randomly pick a seed and then this is used for both the environment and the algorithm. However, like I said before, Atari is actually deterministic. So what we often do in Atari to make it less, we want robust algorithms that can work in general domains. So we don't want to exploit the determinism of the Atari games, essentially. So one thing that's often done is you might take a couple of random no-op actions at the beginning, so that you start off slightly differently. For instance, you might take 30 actions or up to 30 actions that don't do anything before you actually start playing. And this kind of breaks the determinism. In newer versions of the arcade learning environment, which has these Atari games, actually features a possibility to also add noise, which completely breaks this determinism, just to make it a better test bed for algorithms that don't want to exploit that.
So I'm not sure I understood. So is it like the model parameter, like the learning seed with the...
Yeah, so typically we would do, if we would start a new algorithm, you would pick a different random seed for your learning, and this would automatically change everything because your policy would be different. Therefore, your data distribution is different, and therefore, for instance, any randomness that may or may not sit at the environment side maybe already matters less because you're already doing different things in this environment. Yeah?
Is this prone to overfitting on special cases that shouldn't be fit? Like overfit, I guess? Maybe like obscure cases that you only see a few times in the data, but since you prioritize the replay, you see it a lot.
Is this more prone to overfitting? Well, I think there's more generally, if your task allows you to find a certain policy which exploits certain things, it will latch onto that. It will try to find that. I don't think overfitting is so much of a problem in reinforcement learning, because essentially, typically what we do is we have a certain task. Especially in this case, we have a simulator, right? We have these computer games that you can play. Overfitting this game is essentially impossible because this just means you're better at it, right? So you can't really say that you're. So it's less common to have this very clean train set, test set divide in reinforcement learning, because just doing better at the task is just doing better at the task. And that can never be overfitting in some sense. It depends a little bit on your specific setup. So there are cases in which it is a problem. In this case, it's not so much of a problem. Okay, so very many good questions, but I'm going to continue to see if we can cover a little bit more ground. This is another example of something that helped improve things. And for this, I first wanted to just rewrite the update that's done in DQN. This is making it slightly more explicit, something that I said already, which is that we're actually evaluating a certain policy, and what we're evaluating is the greedy policy. But since we're using this target network with this W minus as parameters, we're not actually evaluating the greedy policy with respect to our current parameters that we're actively updating, but we're evaluating the greedy policy with respect to the target network. This is what this argmax means in the middle there. We're picking the highest valued action according to the parameters of my target network, this W minus. And then we're evaluating those actions with that same network. This is a little bit dangerous because now we have these random action values which depend on your learning process and on potentially on noise in your environments, but also just on things like the initialization of your network. And then we're saying we're going to pick something that maximizes that, and then we're going to use the exact same values that we used to pick to evaluate that. This means that it's actually more likely to pick something that is highly valued and therefore get a higher value. It turns out this is a real bias. And there's a way to prevent it very easily in the case of DQN because we already have two sets of parameters. What I did here at the bottom equation, I just colored the black W's we had before. These are the things that we're actively updating each update. I colored them blue, and all the way inside in this argmax, I'm now using, instead of these slowly moving target network parameters, I'm using the online parameters. What this means is I'm now evaluating the greedy policy with respect to my current parameters with the parameters that are more slowly moving. The idea is to break the correlation a little bit between the selection and the evaluation. And this should then reduce this overestimation bias that you might otherwise get. And this turns out to actually really work. This is two Atari games, and what you see here on the x-axis is the estimated value according to your current action values. And the y-axis is on a log scale. And what you see here is that in red, DQN, at some point the values go quite hugely up. And you might think, if you're just looking at the values, you might think, oh, this is good. So apparently I'm learning the values go up, so apparently my policy is improving. But turns out almost exactly at the point where these values start to increase greatly, my actual performance goes down. And there is now a very big mismatch between the actual rewards that you get and the rewards that your value function says it's going to get. This is something you could notice. If you're tracking these statistics, you could basically see, hey, my value estimates are now way overestimating the actual values that I'm getting. If you get rid of this overestimation bias, the performance drop also goes away. So apparently the performance drop was completely due to this overestimation bias in this case, which is kind of interesting. And then if we apply this to all these Atari games, this is basically a performance graph of all of those 57 Atari games. The details are not too important, but if you apply this trick, turns out it works pretty much across the board. So it wasn't just like a random game where this happened. Apparently this overestimation bias was quite prevalent. This was a little bit surprising to me. I hadn't expected it to be so severe. The take-home message I wanted to give in this is that it's good to be aware of the properties of your learning algorithms. In this case, in Q-learning, we're taking the max over something. Then it's good just to stop and think for a moment. What are we taking the max over? What does that mean? What could then happen? In addition, it's very good to track and to analyze statistics. In this case, we could be tracking these action values, and in addition, perhaps the performance, and maybe see, how is my prediction error behaving? Is it going up? Is it going down? It's perfectly okay if your prediction error goes up during learning. This is a little bit weird if you're coming from a supervised learning background, because then you kind of expect that your loss function continues to go down. But in reinforcement learning, because you're changing your policy, it's perfectly acceptable that when your policy improves, your predictions are a little bit outdated and your prediction error might actually go up. This is fine, but at some point it should at least stabilize, go down again, or your policy should continue to improve, both of which you could track. If at some point your values go way up and your prediction error goes way up, but at the same time your policy is not improving, then there might be something wrong. And then you could basically analyze your online statistics to find that out. Yeah?
So isn't that breaking the assumption that the target is constant with respect to the weights?
Yeah, that's a very good question. So aren't we breaking the target network? Aren't we breaking the benefit of the target network in some sense by now making the targets more non-stationary again? So there's actually two ways you could do this. If you look at the equation here, what I mentioned is I wanted to break the correlation. I wanted to break the selection from the evaluation. And there's two ways to do that if you have two networks. We could either pick the greedy policy with respect to my online parameters and then evaluate that with the slowly moving parameters, the target parameters, or the other way around. And it might not be immediately clear which one works better. Turns out this one works much better. And the reason is probably twofold. One is that we're evaluating the policy which is greedy with respect to my current online parameters. And these are also the parameters that we actually use to act with. So it kind of makes intuitive sense that this is also the policy that we actually care about. So it makes sense to evaluate that one. In addition, and perhaps more importantly for the learning process, maybe it's okay if my target change a little bit over time in terms of how the policy changes, and maybe it's less okay if the values also change. And this is what we're doing here. We're keeping the value function fixed. We're just changing the policy that the value function is evaluating. And this is apparently more stable. But this was indeed, I actually did also try the other version because I wasn't immediately convinced that this is the only way that would work.
Yeah, my concern was just about the gradients. Are the gradients going to be different now?
The gradients are going to be different. The updates are going to actually be different. But it's still okay. It's still a reasonable thing to do. And more generally, you could think of this update with the target network more or less is a fine thing to do regardless of the policy that you're trying to estimate. Even if the policy itself might be fairly quickly changing, this is a harder estimation problem. Your prediction errors will be harder if your policy changes very frequently. But in this case, even if we update the parameters, the policy might not change that much. And one way to see that is we're taking this argmax. If your action values are like, if one action is truly, clearly a lot better than the other ones, we might improve the prediction errors on all of these actions, but it wouldn't actually change my policy. So it's not actually clear that my policy is changing that quickly anyway. It will depend on the game, it will depend on the specifics, but it might already be slow enough to be stable. There might definitely be cases in which this is not true. And then it's useful to do those things that I said later, to track statistics, just to keep track of what's working, what is not working, and so on. Yes?
Could you maybe explain what the intuition for using double VQN over VQN is? Like what the general intuition is?
So the general intuition is just to get rid of this overestimation bias. That's basically it. And double DQN, I would say this specific implementation is just one way to do that. If you want to get rid of the overestimation bias in a different way, what these plots basically tell me is that it's about the overestimation bias. If you can get rid of it in a different way, that might be perfectly fine and you might not want to use double DQN. But that's the main intuition. And this is just what I wanted to do here with the update is to basically find the very simplest way, the smallest change to the algorithm to get rid of that overestimation bias. Not necessarily find the best way, but also to keep most of the other stuff fixed so that we understand that it's truly this thing that matters. That was the intuition. Thanks. Yes?
Is there convergence analysis for all those variants?
There are convergence analysis for many of these algorithms, especially for the tabular cases. Before double DQN, I actually proposed double Q learning, which is essentially the same thing. And there's also convergence analysis for that for the tabular case. The off-policy algorithms have less guarantees in the function approximation case than the on-policy algorithms. So for the TD algorithm that Rich talked about yesterday, the pure prediction one, there's also a bunch of convergence results also with function approximation. There are some convergence results with nonlinear function approximation, but already less so. Most of these results, not all of them, but most of these results only concern the asymptotics, which may or may not be of interest to you. It basically tells you whether or not the update is stable. These things are a little bit important, especially to understand the cases when they're not stable, when they might actually blow up and diverge. That said, there are known cases in which combining Q-learning with nonlinear function approximation is unstable and the parameters might diverge. But as we've seen many times in practice by now, if you're careful enough, this doesn't need to happen. The fact that there are these counterexamples doesn't mean that it's inherently unstable and that it will never work, for instance. Yeah, there's a very good book from 1996 by Bartzekas and Tsitsiklis. They call it Neurodynamic Programming, and this is essentially about reinforcement learning with function approximation. They have a lot of results. There's a newer book by Bartzekas from 2007, which basically has an updated version of many of these results as well, and much more. If you're interested in that kind of thing, those are good pointers. In addition, there's a shorter book by Csaba Szepesvári, who also will be speaking here later today. And he has he's done much work in this area as well. Okay. Oh yeah, the last point I still wanted to mention. If you understand what the problem is, in this case the overestimation, sometimes you can do a very simple thing to fix it. And for instance, in DoubleDQN, one of the reasons why I specifically did this one, it's a one-line change of code. And that's very nice. If you can just, okay, it's just a hypothesis. If I change this, I'm going to change this property. Then you can inspect, and then you know what you've done, and you know what the impact is. Changing too many things at the same time, it might work, but it's much harder to understand what happens and why these things work. And then it's hard in the next problem to know exactly what you need to do. This fits into a more general theme that I would just wanted to highlight. There's two of these things that are a little bit related, but different views on the same thing. The target networks and the experience replay, you could view them as deep learning aware reinforcement learning. We're basically changing the updates a little bit to be more similar to what we know that works with deep learning. The experience replay, in some sense, makes it more IID, and we know that that's something that these deep networks in nonlinear functions in regression like. The target networks make the targets more stationary. We know that that's something that these systems work well with. Similarly, but in the opposite view, is reinforcement learning aware deep learning, where maybe you want to change, say, the optimizer that you're using. Maybe you want to change your network structure to be more conducive to what you're trying to do with this. And on that second note, here's an example of that, which is dueling DQN. The actual paper title is a bit longer, Dueling Network Architectures for Deep Reinforcement Learning, from last year's ICML. The idea is very simple. You can think of the action value function as a combination of the value of the state under a certain policy. All of this is under the same policy. This is the first equation over there. Plus the advantage of picking a certain action. And for simplicity, let's just say that these advantages are zero mean. That means that their value function is now basically learning the offset. How important is it to be in this state? And the advantages then learn how much of an advantage do you get in terms of value for picking this specific action in that state. Now you could write it down slightly differently, which is the second equation there. And what's being done there is essentially taking away 1 degree of freedom. This is essentially making sure that these values, the value function, indeed is trying to estimate the baseline, assuming that the advantages are roughly zero mean. And then if you want to have accurate Q values, these advantages will almost automatically then navigate towards being zero mean to fit nicely within the loss that we're specifying. Now what's kind of cool about this is that we have action values back, right? We've just basically decomposed the action values in a specific way. And one way to implement that is just to change the network structure. And this is what's depicted there at the bottom. The first thing that you see there is the typical DQN network, where there's a conv layer or a couple of conv layers, and then there's a fully connected layer. In the dueling network architecture, it's exactly the same, but we split the fully connected layer, and then we go into a value function and into these advantage functions. We just add these together to get our action value functions, and that's all. And then we do the same double DQN update with prioritized replay or without prioritized replay on top of that, and this works. this helps, which is kind of interesting because all we've done is change the network architecture. We didn't change the update in any other way. But by changing the network architecture, we give a bias to the system to represent things in a certain way, and this way happens to be a good, nice way to represent the value function. And what I'll show you now with this video, I hope it's a little bit visible. What you see on the left-hand side here, this is a game of Enduro. It's a racing game from the Atari suite of games. And what you see on the left here is basically the gradient with respect to the inputs of your value function. This is sometimes called a saliency map. One way to think about this is what my algorithm is paying attention to get the value. And what you see is that the vision, in some sense, the saliency, is all the way at the end of the road, where the road is heading towards. The right-hand side is the advantage functions. It's basically what are the advantages of every action paying attention to. In the current screen, you don't see any red. There's nothing there. But if you watch while I press play, you'll see it flash sometimes. And maybe I can actually stop it. Well, I was slightly too late there. Maybe I can grab another one. So sometimes you see it flash when there's cars nearby. I'm not grabbing it. Oh, I'll just leave it. Interestingly, it seems that the value function is paying attention to things that happen way at the end, whereas the advantages are mostly paying attention to things that happen very close by. This makes sense because the action differences between different actions are much more pronounced when there's cars nearby, when it actually matters to your value which action you take. Most of the time, it doesn't really matter that much which action you take. If there's no cars nearby, it doesn't really matter. You could pick any of them. The differences are very small. And what we see here is essentially that the system has now learned to use different parts to pay attention to different parts of the problem. And this then helps performance, turns out. Again, this is a very simple change to the algorithm. It's not even to the learning updates, but just to the network architecture, and this helps performance because we know that it has a certain semantics to it. We know what it's trying to do. Yes? The target for the value and the advantage? Yes, it's the latter. The question is, do we have separate targets for the value and the advantage, or do we just have one target for the Q functions? It's the latter, but actually you could write this down because it's just gradient descent, so you could write this down as a squared loss on your Q values, and you could decompose that into basically a loss on your value and a loss on your advantage, but these are now related, these two losses, right? They depend on each other because the actual loss is on the action values. That's a very good question. Yeah? So why do we get rid of the average advantage in the Q value? So the idea there is that we want the value function, we basically want to force the value function to really be the value of the state, and the advantage is just to be the offset. So we kind of want the advantage to be zero mean. And this is one way to do that, because in order for this value function to be accurate, because we're deducting the mean advantage, it needs to be that value. It can't just be an arbitrary thing. If you don't do this, you have an additional degree of freedom. What this means in practice is that, for instance, you could increase all your advantages and decrease the value and get exactly the same Q values. Turns out if you run that in practice, it doesn't seem that harmful, but it turns out it works less well. It's not maybe completely clear or understood why, but it makes a little bit intuitive sense, and then in practice it does turn out to be important. It's a good question. Yeah?
We also see that it seems to focus on the score, on the written score.
Sorry?
There is some red on the scores.
Oh yeah, so many of these algorithms actually pay attention to the score that's on the screen. It's not completely clear why, but in some games it might actually be a very good indication of how much more reward you can accrue. For instance, how far along in the level you are. Sometimes these scores can almost be seen as kind of like a clock. But it depends on the game, and I honestly don't quite know why it's paying attention to it here in Enduro. But it's quite a common thing. We see that a lot. Yeah. Yes?
Is this having an effect of doing some sort of smoothing? Like if you were to put some partial cooling over the actions, and we were to shrink it around the knee, would that have a similar effect, or this is not? This isn't really from smoothing.
So this is a form of smoothing. I don't know. I hadn't thought about it like that. I more just see it like a semantic decomposition of the value into two different parts. Maybe there's something there. Maybe there's also like a small So what I would encourage, especially if people start playing with these things, is for instance to take a hypothesis like this, or maybe this is good because it's doing some form of smoothing, and maybe then there's a way to do just the smoothing, like a very, very constrained way, and see if that also helps, or whether this has a similar benefit. I don't immediately see it here, but okay. So mostly running out of time. So let's see what, let's skip that. There's one more thing that I wanted to mention. This is mostly stuff that Peter Beals talked about yesterday with the policy gradients. This is the same derivation that he had on the slide, so I'm not going to go through that again. But I just wanted to highlight again that there's different ways you could learn a policy. And one way is to do that directly. And let me just jump in basically here. The algorithm here is called reinforce. It has different names, but one common name is reinforce, which is from a paper from 1992. And it gives you a sample-based way to update your policy. This is different from what we talked about before. Because we're not learning a value function anymore, we're directly updating policy. And the important equations here, so the first one here, the first equation here basically says J here is maybe standard notation in some parts, but you can just think of this as the value of your policy under those parameters, basically across states. So J doesn't depend on state, but just think of it as the expected value across all states. And then turns out this derivation that we had before that Peter talked about yesterday basically shows us that we can sample that thing, which is where you see on the right-hand side that there's an expectation around something. And this expectation has the true Q value in there and the gradient with respect to the logarithm of your policy. What this essentially means, one way to think about this, is that what happens to your policy parameters is if your value function is high, you should increase the probability of selecting that action. If it's low, you should either decrease the probability of selecting the action or just increase it less, and then by normalization it turns out to decrease. And this is the whole idea behind the reinforced algorithm. You could add a baseline, which typically is just the value function. This reduces the variance, but it doesn't change the direction of your gradient. So this is a fine thing to do. Peter also mentioned this in his talk. And the intuition is still exactly the same. We're still increasing the probabilities of actions that were better than expected with respect to the baseline. And then we're decreasing the probability of actions that were worse than expected with respect to our baseline. It's not unclear that the baseline needs to be very accurate, because otherwise we would just be increasing certain actions and others less. And then in the net effect is maybe still the same, but picking a good baseline is important for the variance of the system. Yes?
How exactly does the baseline decrease the variance?
It's a very good question. So how does the baseline decrease the variance? The idea is actually quite similar to the dueling architecture that I just showed you. The baseline here basically keeps the variance due to the states out of the system. The returns will have variance because your actions will give you like a random return, and maybe the system is also noisy, so there will be variance in that. But in addition, the states might all have different values, and this just gives you additional variance if you don't take this out. So this is basically the way to think about it. The randomness due to which state you're in is taken care of by the baseline, and therefore the variance is lower. Okay? So I'm skipping over this. This is about can you do replay in that setting? You can, but let's first talk about when we don't do replay. So what is an alternative to doing replay? So think about why we were doing replay. This is again about talking about what are the properties of these algorithms. When do we expect them to behave well? Why we were doing replay in the first place? Well, there's two reasons. One is data efficiency, but the other one was we want the data to be a little bit more diverse, more like what we know that works well with deep learning. But there's more than one way to do that. And this is a different approach. You could think also about just having many simulations happening at the same time, and having more or less your same agent acting in all of these simulators at the same time, in parallel. This would also give you diverse data. in a completely different way, but it's still diverse data, so maybe this still works. And then this was investigated by Vlad and others, and they found that this does really work, even if you just then pretty wildly update the parameters from all of these different threads which are happening asynchronously on a single machine, on many CPUs perhaps. And you can basically combine this with any reinforcement learning algorithm. This is like a separate thing. Whether you do replay or whether you do this parallel environment thing, this is separate from whether you do, say, reinforce or Q-learning. They both are combinable with each other. And this turns out to work really well. I'll skip through this, but I'll show you a slide. This is the slide I wanted to show you, where now at the bottom left you basically see these networks, which now have two heads. One is a policy head, and one is a value head. This is similar to this dueling network architecture, but instead of having advantages and a value, we now have this policy and a value. And then we can use the reinforce updates or an approximation thereof, which is the equation there at the top equation on the right, where we don't take the full return, but we reduce the variance even a little bit further by bootstrapping a little bit short. You could do the one-step version, but you could also do the multi-step version, which was used here. And then you could basically tweak how many steps you do to get a good trade-off between the variance and the bias. And I just wanted to highlight this for its similarity, and also that it's a different approach to do something similar, to get the similar benefits as from the replay. I understand we need to stop here for coffee, but feel free to come up to me for questions. Thank you.